In section 11.2, we're looking at areas of trapezoids, rhombuses, and kites. The first shape we're going to look at is a trapezoid. Our formula for a trapezoid reads 1/2 the height times base 1 plus base 2. Now if we look back at a trapezoid, remind ourselves of some things that work here. We do have two bases in a trapezoid, and those are the parallel sides. There's nothing mentioned about them being congruent. In fact, they won't be congruent. They're just a pair of parallel sides. I've numbered them base 1 and base 2. It doesn't matter which one's which, just identify them, keep them separate. Eventually you're going to add them as we see in the formula. The height is perpendicular to this base as well as the other base. Even though the height is a vertical length here, we want to keep in mind the height is that distance between the bases. So it's that distance inside the trapezoid that's perpendicular to both bases. We also have this side out here, which we probably should just call the leg, and we have those in the trapezoid. If that is not perpendicular to the bases, we can't use that as a height. We're going to get to this example over here in a minute, but in this case, this 4 is all a leg and the height. We could even draw it in here as a 4 as well. So in that case, it does work, but for example, if they give this value as a 4, we wouldn't call that use that as the height, so it needs to be perpendicular. Now, the way we got this formula is actually using the mid-segment of a parallelogram. Not the mid-segment parallelogram, the mid-segment of a trapezoid. And that's where we found the midpoints of the legs. We draw a mid-segment, and by that, we know the mid-segment is 1/2 base 1 plus base 2. Well, if we draw that mid-segment and then we draw a rectangle with that, with the same height, we actually have this rectangle that overlaps the trapezoid, where we could then take this extra triangle on each side and fit it into the rectangle. So in that sense, this 1/2 height times base 1 times base 2 really becomes the mid-segment times the height, or in a rectangle, which would be base times height. So it's related to a rectangle in that sense, but this is going to be our formula for the trapezoid. So let's look at a few different examples that use it. In our first one here, like I already mentioned, 4 is our height, and we have our two bases. Make sure you get in the good practice of writing the formula out each time using the letters before you start plugging numbers in. That is a good habit to have, and it's what you should be doing. Then I can plug in what I know. I have the height is 4. Base 1 and base 2 would be 6 plus 8, but really if I wrote 8 plus 6, it's the same thing because I'm eventually going to add them. Get 14. I could take half of 4, I could take half of 14, I can multiply 4 times 14, then divide by 2. In either case, it'd be 2 times, got ahead of myself. 2 times 14 gives me 28 feet squared. Make sure you write your units for area problems. That would be feet squared. Moving on, we have a couple more examples to look at. We're still going to use the same formula, but kind of approach it a little differently. In the one on the left, we have use the given information to find the value for x. So in this case, they give us the area is 300 meters squared, and it looks like we're solving for x, which is one of our bases. In this example, notice that 20 is the height of the trapezoid. Even though it's not a vertical length here, it is still the height because it's the distance between the bases. So area equals 1/2 height times base 1 plus base 2. I plug in what I know, and I could write x plus 10 or 10 plus x. It doesn't matter necessarily. What I'm going to do first, I'm going to take half of 20. Get to here. Now if you wanted to distribute the 10 times x plus 10 and get 10x plus 100, you could do that. But what I'm going to do is divide both sides by 10 and get 30 equals x plus 10, which gets me to x equals 20 meters. Make sure you write your units. We're talking about a length here, not an area, so it'll just be meters, not meters squared. Okay, moving on to our next one. We write our area formula because we know it's a trapezoid, and just get in that habit. When you look at the shape, this is what shape it is, this is the formula I'm going to use write it, and maybe if you have to do some extra work, which we'll probably have to do here, you at least already have it started so you can see what you need. If I look at the shape, I have a base. One of the bases is 8. The other base is this total up here, which is 20. The height, well, doesn't look like I have the height. That would be this value here. 15 is not perpendicular to the bases, and we want to look for perpendicular whenever we're kind of multiplying. It's just a common trait all those area formulas have. Whenever we're multiplying values, they are perpendicular to each other. So I can't use that 15 there. But if I'm looking for the height, I actually have a right triangle in here. And this right triangle is going to be the key to help me find the height, because I have 9, h, and 15. So, looking at that right triangle, I could use Pythagorean theorem and say 15 squared equals 9 squared plus h squared. 225 equals 81 plus h squared. 144 equals h squared, so h is 12, which is now my height. I can plug that in. I have 1/2 12 times 28. Take half of 12, I get 6 times 28, which is 168. Going to be units squared here because we don't have feet or inches, so just a generic units squared. Okay, so on to our next shapes here, and these are actually a 2-for-1, a rhombus and a kite. They're going to have the same area formula. Now, the formula is going to be 1/2 diagonal 1 times diagonal 2. We're not using the sides here. If we look at the diagonals, first of all, for each of these, let's label them. I have diagonal 1, diagonal 2, and again, it doesn't matter which ones you number 1 and 2, as long as you just use both diagonals. But things I know about the diagonals, I know that they are perpendicular. And going with that common trend we're seeing with these area formulas is they need to be perpendicular for us to be multiplying. Again, that's not a rule we're going to state, but it's just something to look for. Make sure they're perpendicular because that seems to be the case on all these formulas. Now, diagonal 1 times diagonal 2. Let's look at the rhombus on the left. Because really they're the same general shape. The only thing is that on the kite, these values are different from this diagonal, whereas on the rhombus, they're all split and they bisect each other. But if I were to multiply diagonal 1 times diagonal 2, this would actually give me a rectangle, because it would be like base times height. So if I did that, I would have this rectangle. But if I look at the area of the rhombus, or even the kite, if I did that, it doesn't fill up the rectangle. If I went further and broke it into 4 quadrants, in each of those quadrants there's a smaller rectangle and a triangle that's a piece of the rhombus. That triangle is 1/2 base times height, where the whole thing here would be base times height. So this triangle is half of this quadrant. This triangle is half of this quadrant. Same here and same here. So with that logic, looking at the whole rhombus, it's half of the whole thing, which is the rectangle, which is why we have that 1/2. If we strictly multiply diagonal 1 times diagonal 2, then, well, we would have a rectangle. We don't want the rectangle. We can't count this empty space here. We have to take half of it. So 1/2 diagonal 1 times diagonal 2 will be our formula. Let's look at a couple examples of it. Starting with our first shape on the left, that is a kite. They've shown our diagonals really 2 different ways. They have the brackets showing the 14. That is typically the way we'll see diagonals. They also drew the 6. Make sure it's the entire length. That's the diagonal. We typically won't see both of them marked inside just because it gets a little jumbled, and we want to make sure if we're talking about part of it or the entire diagonal. So we have 1/2 diagonal 1 times diagonal 2. I can plug in 14 times 6, which gives me 7 times 6, or 42 inches squared. In my next one, this is a rhombus, and I can write my formula first. And when I look for my diagonals, it's not 40 and 30, because that 40 is this right side of it, which means there's another 40 here, because they bisect, as well as another 30 down there. So in fact, my total diagonals are 80 and 60. So now when I solve, it's 1/2 60 times 80, which is 30 times 80, or 2,400 meters squared. Now, you may say, well, I'm going to take half of them, so I might as well just keep the 40 and the 30. Not the case here, because as you notice in the formula, we only take half of one of them. We can't take half of both, because that would throw off our answer. So, get the entire diagonals, plug them into the formula, and let the formula do its job. Unless you're going to break it up, and really I could here find the area of each triangle and multiply it by 4. With that idea, each triangle is 40 and 30, which, if I did that one, it's 1/2 30 times 40, which ultimately is 600. So each triangle there is 600. I have 4 of them. 4 times 600 would be 2,400, which would also give us our answer. Okay, if we look down at this next problem, it's now talking about finding the area on a graph. So if we just sketch out the basics here, I have 4 points. I have a point at 1, 3, that's M, 5, 5, that's N, 3, 9, or 9, 3, I should say, is P, and 5, 1 is Q, and that gives us our rhombus. Now, it wants us to find the area. When we've seen this before, we may have had to use a distance formula to find the length of these sides. We also saw this back in our chapter with parallelograms. Maybe we'd have to find slopes and use them there. Not quite the case here. This one's actually going to be a little bit nicer, because to find the area of that rhombus, we don't need the side lengths. We need the diagonals. So, if I look at NQ, NQ is the diagonal. NQ, if I look at both points, I have 5, 5, and 5, 1. And what I notice is they each have the same x value. They each go over 5. N then goes up 5, and Q goes up 1, which means if this one's at 1 and this one's at 5, they're 4 apart. So that's one of my diagonals. Between M and P, it's 1, 3, and 9, 3. They each have the 3 in common this time. They each have a y value of 3, meaning they each go up 3. So, one's at 1, the other one's at 9. That means they are 8 apart. So it's my other diagonal. So 1/2 4 times 8 gives me 2 times 8, or 16 units squared. So good luck on these problems. Make sure you're picking the right formula. Whenever you're going to a trapezoid, be sure that you're looking at your height is perpendicular to the bases, and you choose the correct formula. Remember, 1/2 height times base 1 plus base 2. And when you look at a rhombus and a kite, be sure when you're looking, it's the full length of the diagonals. I don't want just the part of it, I want the entire thing. And also something to be aware of, if they give me a side out here, I may have to use Pythagorean theorem to get the new side value. In fact, let's look at one of those real quick. Let's just sketch one. Not the greatest sketch here, but let's say that is a kite. I have a side length of 4 here, or 5. This is 4, and that's 10. And I need to find the area. Let's mark our kite here. So we know it's 1/2 diagonal 1 times diagonal 2. One of my diagonals is 14, so I know that much. I need the other one. I need to know this length. Now, in a kite, this segment and this segment are the same, because that diagonal happens to bisect them. So I know whatever they are, they're the same. So I need to find that piece. And we're going to use this triangle here to help us, because I have 5, 4, and just call this x. I can use Pythagorean theorem there to get 5 squared equals 4 squared plus x squared. 25 equals 16 plus x squared, so x squared comes out to be 9, and x is 3, which means this is also 3, so our second diagonal is 6, and now when we can solve, it comes out to be 7 times 6, or 42 units squared. So be on the lookout. If they give you a side, ask yourself, am I going to need that to find the diagonal? Because typically for the area formula, we will not need that for a rhombus and a kite.